Welcome to Exnoesis. Take a deep breath with me, in and out. Let your being settle as we drift. Have you ever looked at the night sky and felt overwhelmed by how impossibly small you are? That profound feeling when your mind grapples with reality's sheer scale. When you realize you're on this tiny rock, a pale blue dot, hurtling through a dark ocean so vast your brain refuses to process it. It's a sensation beyond logic, a primal awe whispering of horizons beyond our grasp. Settle in, dear friend. Let your thoughts unfurl, because what we'll explore together will gently reshape every assumption you've held about size, distance, time, and your own delicate, yet significant, place in existence. The universe isn't merely big like a mountain or large in human terms. It is so incomprehensibly vast that even our most advanced scientific measurements can sound like impossible fiction. We're talking distances so colossal that light itself, the universe's speed limit, takes billions of years to traverse tiny fractions of it. Imagine a photon, birthed in a primordial star, racing across the cosmos, only to arrive now as a faint echo from a time before your galaxy existed in its current form. And here's the twist. What we can truly perceive might be just a droplet in the silent ocean of what's really out there. Tonight, we embark on an ultimate journey of the mind. A voyage through all space and time. Our start? Your room. Our destination? The edge of everything known, and perhaps beyond. We'll uncover structures so grand they make our Milky Way galaxy, that swirl of billions of stars, look like a grain of sand on an infinite beach. We will stretch our minds to grapple with the reality that the universe might be infinite. If so, it carries a poetic implication. Somewhere in the swirling expanse exists another you, listening to these words, pondering these same questions. By the time our meditation concludes, you'll understand why brilliant minds dare to whisper the thought. We might be living inside something bigger, stranger, and more mysterious than we've ever dared to imagine. But first, a soft warning. This journey will gently mess with your head. The numbers are so large that mathematicians invented new ways to write them. The concepts are so bizarre and counterintuitive they sound like science fiction. Yet they are not. They are the unyielding reality of the universe we inhabit. So if you've ever wondered how insignificant you are, or if you yearn to have your worldview gently demolished and rebuilt with cosmic wonder, then stick around. Relax your mind, soften your body, and let your curiosity expand, because what you're about to learn will change how you see everything, forever. Now, let the cosmic symphony begin. Our journey begins not at some distant boundary, but right here, where we stand. We are on Earth, a living sphere which, in the cosmic scheme, is a tiny speck of dust. Its significance, compared to our solar system, let alone the immensity of our Milky Way, is vanishingly small. Consider this. Our Sun is but one of at least 100 billion stars in our galaxy. A vast proportion of these distant suns will likely host their own planetary systems, each a tiny cosmos. But the true, terrifying scale of the universe doesn't reveal itself until we escape the bounds of our own Milky Way. When people speak of space, they're usually referring to what astronomers call the observable universe. This region is also known as the Hubble Volume. Imagine a gigantic sphere centered on Earth. This bubble encapsulates every galaxy, star, and wisp of matter that our instruments can ever hope to observe. Why? Because the light from these distant bodies has had just enough time to travel across the expanding void and reach our solar system. We know light travels omnidirectionally at a finite speed of just under 300,000 kilometers per second, or roughly 186,000 miles per second. This speed is exceptionally fast on any earthly scale, yet over colossal cosmic distances, it becomes paradoxically, agonizingly slow. Any intergalactic journey of light incurs a substantial, incomprehensible delay in reaching Earth. It's a cosmic game of telephone played over billions of years. This inescapable delay is why distant objects appear to us not as they are now, but as they were billions of years ago. This is why astronomers use light years as their unit of measurement, a measure of both distance and time. If a galaxy lies a billion light years away, the image we see reveals it as it existed 1 billion years in the past. It is a beautiful specter from another epoch. In this sense, the edge of our observable universe is not just a spatial boundary, it is a time barrier, constrained by the universe's finite age of approximately 13.8 billion years. The Hubble Volume, therefore, contains only those galaxies whose light has journeyed for less than 13.8 billion years to reach Earth. The farther away a galaxy is, the closer its light appears to the birth of the universe, 13.8 billion years ago. Thus, our journey to the edge of the observable universe is also a journey back through time, to the primordial beginning. An old saying goes, "A telescope is a time machine." A telescope like the James Webb is more than that. It's a TARDIS whose sensitive infrared eyes are piercing the veils of distance, staring further back into time than humanity has ever managed. This allows us to map the cosmos at every stage of its immense life. Throughout its 13.8 billion year life, the universe has been relentlessly expanding. We see evidence of this ingrained in the light from deep space. This ancient light, having surfed an expanding spacetime, arrives elongated and reddened due to a phenomenon called redshift. Redshift occurs when photons traveling to Earth experience a decrease in wavelength because the fabric of space they traverse is expanding. It widens the gaps between the crests and troughs of the traveling light waves. Imagine space as a slowly inflating balloon. As this balloon inflates, the creation of new space widens the gaps between all objects, including waves of light. This stretching shifts visible light towards the red end of the spectrum, hence redshift. This phenomenon affects all electromagnetic radiation and serves as a reliable corroborator of intergalactic distances. The redshift value of an object, denoted by Z, provides us with an intrinsic scale for our cosmic journey. The higher the redshift, the farther away, and the further back in time we are gazing. It's crucial to internalize a distinction. While the light travel distance is about 13.8 billion light-years, tied to the universe's age, the present-day proper distance to those same objects is much greater. Due to the continuous expansion of space, the observable universe is a sphere roughly 93 billion light-years across. This means galaxies whose light we perceive from 13.8 billion years ago are now, in their current locations, some 46.5 billion light-years away from us in every direction. They have been carried further by the cosmic tide. This staggering fact highlights the cosmos's immense scale even within what we can theoretically observe. This volume is estimated to contain an astonishing 2 trillion galaxies. 2 trillion. Each a majestic island of stars, potentially containing hundreds of billions of suns. Each potentially hosting planetary systems. The sheer mathematical scale of this can make your head spin with wonder. Let us begin our galactic journey. Consider your hometown. It feels substantial, does it not? Thousands, perhaps millions of lives interwoven. Now zoom out until your entire country appears as a tiny patch of land surrounded by vast oceans. Keep zooming, and Earth itself shrinks to a glistening jewel in the black void of space. At this distance, your hometown has vanished. Yet, we have barely begun our journey. Let's pause and consider our solar system. It seems expansive, wrong, utterly wrong in the cosmic context. Let's try a thought experiment. If the sun were a basketball in the middle of a football field, Earth would be a grain of sand orbiting it at 25 yards. The very edge of our solar system, where icy comets begin their journey, would be roughly 4 miles away from that basketball sun. 4 long, silent miles of mostly empty space. That is our entire cosmic neighborhood, where every human has ever lived. And yet, this domain is so small that from the nearest star you wouldn't even discern its presence. Now, here is where our journey introduces unsettling truths. The nearest star to our Sun is Proxima Centauri, about 4 light-years away. A light-year is the distance light travels in 1 year, roughly 6 trillion miles. So Proxima Centauri is about 24 trillion miles away. To put that in perspective, driving a car at highway speed toward that star would take you approximately 30 million years. That's longer than the recorded history of human existence, and this is merely the distance to the nearest star. Our Milky Way galaxy contains an estimated 200 to 400 billion stars. Most are vastly farther away than Proxima Centauri. The Milky Way itself spans an average diameter of 100,000 light-years. To grasp this, imagine sending a text message to the opposite side of our galaxy. Traveling at light speed, it would take 100,000 years to arrive. But here is what will blow your mind. Our galaxy is, by cosmic metrics, simply average. It's not particularly large or small. There exist galaxies out there that make the Milky Way appear utterly pathetic by comparison. Consider the galaxy IC 1101. This sprawling elliptical behemoth, over 1 billion light-years away, is 50 times larger in diameter than our Milky Way. It contains over 100 trillion stars. That is more stars than there are cells in your entire body. Yet we are not finished. These galaxies are not scattered randomly. They are organized into gravitationally bound groups and clusters, forming the large-scale structure of the universe. Our Milky Way is part of the local group, a neighborhood of about 80 galaxies spanning roughly 10 million light-years. However, this is a preamble to the massive galaxy clusters that pepper the universe. Consider the Coma Cluster, a metropolis of over 1,000 galaxies, or the Perseus Cluster with over 3,000. These titanic clusters are held together by the gravity of their combined mass and the influence of dark matter, forming structures that stretch for hundreds of millions of light-years. And the clusters themselves are woven into even larger structures called superclusters. We find ourselves within the Laniakea Supercluster. Its name, from Hawaiian, means immense heaven, a fitting moniker for a structure encompassing 100,000 galaxies across 520 million light-years. To traverse this supercluster, a photon would have to journey for over 500 million years. That means light leaving one edge today won't reach the other until long after our Sun has exhausted its fuel and our Earth has been reduced to cosmic dust. While galaxies within Laniakea are not gravitationally bound in the same way as stars in a galaxy, the combined gravity within this network induces detectable movements. It's a slow, majestic current. For a long time, we didn't know what these galaxies were stretching toward. The source of Laniakea's gravitational basin was obscured by the dusty plain of our own Milky Way. Therefore, the source of this collective pull, the so-called Great Attractor, remained an enigma. But new surveying capabilities have helped illuminate this previously hidden zone of avoidance. Unlike visible light, X-rays and infrared emissions can pass through the thick dust of our galaxy. This allows us to detect the superclusters lying beyond and reveal the source of the Great Attractor. We found it within the Hydra Centaurus supercluster. At its heart, 250 million light-years from Earth, we discovered the Norma cluster. This dense aggregation appears to be the gravitational nucleus of the Great Attractor. However, this cluster alone is not substantial enough to account for the speed at which galaxies are attracted toward this basin. This suggests something larger is also exerting an influence. Indeed, beyond Laniakea, over 650 million light-years away, we encounter the Shapley Supercluster. This is a massive supercluster, a dense concentration of thousands of gravitationally bound galaxies. And farther beyond that, at over 870 million light-years, we find the Vela Supercluster. It's now believed these two more potent superclusters, Shapley and Vela, are exerting cumulative influences on Laniakea's galaxies from afar. They amplify the gravitational potential of the Norma cluster. This complex interplay explains what makes the force of the Great Attractor so truly great. This invisible monster is gently dragging our Milky Way and its vicinity through space, like debris in an enormous gravitational whirlpool. The Laniakea Supercluster is not gravitationally bound in the same way a galaxy or dense cluster might be. So is it accurate to call these higher-order aggregations structures? The debate hints at the complexities of cosmic organization. However, the tendrils of matter within the cosmic web can reach even larger scales. These are known as galaxy filaments. These filaments represent the largest known type of structure in the universe, colossal chains of galaxy superclusters stretching over distances exceeding 250 million light-years. Imagine the largest structure you can conceive. Then imagine it is but a single thread in an unimaginably vast spiderweb, a cosmic tapestry stretching across the observable universe. When the cosmic web is visualized, it presents an eerily familiar pattern. Picture the interconnected neural networks in your brain. Now picture the largest structures in the universe. They appear strikingly similar. Vast filaments of matter connecting dense nodes of galaxies, with enormous voids in between. It is as if the universe is organized like a gigantic brain. This similarity might be more than a coincidence, a possibility we will return to later. A staggering 1 billion light-years from Earth, at a redshift of 0.074, we encounter one such entity, the Sloan Great Wall. This is a colossal, filament-like structure first identified from the Sloan Digital Sky Survey. This structure is a giant, arcing formation of countless galaxies. It contains several intensely packed superclusters, the largest designated SCI 126. The full structure measures more than 1.3 billion light-years by its largest extension. While its scale is undeniable, it has been argued that this enormous structure may be a chance alignment of three distinct superclusters and filaments, rather than a single continuous chain. Nonetheless, upon its discovery in 2003, the Sloan Great Wall was crowned the largest known cosmic structure, a title it would hold for a decade. As we pass through the Sloan Great Wall, our journey carries us deeper into the cosmic past, reaching the boundary of redshift 0.1, about 1.38 billion light-years from Earth. Beyond this, our light delay exceeds 1.5 billion years. From this vantage point, we perceive objects more characteristic of the younger, more energetic universe. Billions of years ago, galaxies like our Milky Way were undergoing violent evolutionary changes. They were engaged in a cosmic dance of collision and merger, combining their stars and gas in a tumultuous process. These mergers flooded the central cores of these galaxies with star-forming gas, igniting a furious burst of star birth. When a colossal amount of gas collects at the center of a galaxy, around its black hole nucleus, an array of energetic electromagnetic processes can arise. When a galaxy's central black hole interacts with this dense gas, we call it an active galactic nucleus, or AGN. This interaction leads to the release of an unfathomable amount of radiant energy, powerfully amplifying the galaxy's luminosity, particularly in the radio spectrum. Radio galaxies are one type of AGN. These colossal emitters of radio waves occur within older elliptical galaxies. As gas orbiting the galaxy's nucleus is pulled inward and ionized, its subatomic particles become entrapped in the powerful magnetic fields around the black hole's core. This matter, superheated and accelerated to unimaginable energies, is blasted away from the black hole's event horizon at velocities approaching the speed of light, forming a pair of spectacular relativistic jets. These jets can extend for thousands of light years into space, dwarfing the galaxy that birthed them. This stream of ejected material glows with a brilliant radio-loud synchrotron radiation. Thus, radio galaxies become more detectable at higher redshifts, further back in time and distance than fainter radio-quiet galaxies. On the boundary of redshift 0.1, we identify 3C327, a powerful radio galaxy. And another 1.5 billion light-years deeper, we encounter the current largest known radio galaxy, Alcyonius, whose radio emissions extend a whopping 16 million light-years. But between these two, at a redshift of 0.158, we find an even more extraordinary entity, 3C273. This is not just a radio galaxy, it is a quasar, the brightest, most energetic type of AGN known. Unlike a radio galaxy's jets, a quasar's luminous radiance is fueled by the ferocious activity within the immense accretion disk whirling around its central supermassive black hole. Within this disk, torrents of subatomic particles race at relativistic velocities. They constantly smash into other particles, unleashing prodigious amounts of thermal energy through friction. This friction superheats the material to millions of Kelvin. This incandescent material then radiates colossal amounts of electromagnetic energy and light with staggering efficiency, some 50 times more efficiently than the nuclear fusion in our Sun. This process releases unfathomable quantities of radiant energy across the entire electromagnetic spectrum. Quasar galaxies shine hundreds of thousands of times brighter than an entire galaxy like our Milky Way. Their power is so immense they can impersonate, from billions of light-years away, the appearance of mere stars in our own galaxy. The first quasars were discovered because of their unexpected prominence in other wavelengths, specifically 3C273's powerful radio and ultraviolet emissions. However, despite their luminosity, quasars are infrequent in the closer, lower redshift universe. 3C273 lies about 2.5 billion light-years away, but the vast majority of quasars are found further back in cosmic time, in an earlier epoch more suited for their ignition. In addition to requiring an abundance of gas and dust, a black hole must have a particular range of sizes to drive a quasar's emissions. If a supermassive black hole is too massive, its gravitational pull would be too broad to effectively shred in falling gas. Instead, it gulps material whole, rather than the chewing action required to create an incandescent accretion disk. This chewing motion, the intense tidal gradient exerted by smaller, yet still supermassive, black holes, spaghettifies infalling gas, tearing it apart and feeding its accretion disk, fueling the quasar's luminosity. Thus, when we peer back into the earlier universe, where black holes were generally smaller, we observe a greater abundance of these quasars. But to witness quasars in their greatest abundance, we need to venture much further into space. As we traverse the boundary of redshift z equals 1, just under 8.4 billion light-years from Earth, we peer into an epoch when the universe was younger, smaller, and more dense. At this point, quasars burst into view at dramatically higher rates. This heightened prevalence is convenient for astronomers, as the light from ordinary galaxies at these depths is incredibly faint. However, quasars, shining from the peak quasar epoch about 10 billion years ago, can brilliantly illuminate the nascent galaxy filaments upon which they once shone. They act like luminous markers, outlining the earliest skeletal structure of the universe. As we approach 9 billion light-years from Earth, our observations reveal quasar galaxies in vast formations that emulate the colossal cosmic structures we encountered in the closer universe, such as the Sloan Great Wall. These aggregations are known as large quasar groups, LQGs. They are vast assortments of quasars scattered across multi-billion light-year distances. While the groupings are not believed to be gravitationally linked, their sheer size ranks them among the largest structures we've discerned. Peering 8.8 billion light-years from Earth, we encounter the first of 3 record-breaking quasar groups, U1.11. This grouping contains 38 quasars spread over 2.2 billion light-years. Then, at a redshift of 1.28, we find the closed Campusano LQG, a congregation of 34 quasars spanning over 2 billion light-years. And finally, around that same distance, we find the largest grouping of them all, the huge LQG, a staggering assortment of 73 quasars distributed across an expanse exceeding 4 billion light-years. It must be acknowledged that none of these assortments are likely real gravitational structures. They are more likely the product of random alignments. Nevertheless, scientists rank these 3 quasar groups among the largest known structures ever observed. However, the very largest structure ever identified, the entity that displaced the Sloan Great Wall in 2013, is not a quasar group. It is the Hercules-Corona Borealis Great Wall, a gamma-ray burst formation. A gamma-ray burst, or GRB, is the most powerful electromagnetic explosion known. These fleeting events release as much energy as our Sun's entire life cycle in mere seconds. Unlike quasars, GRBs don't tend to be associated with active galactic nuclei. Instead, they often arise from cataclysmic supernova explosions, or when a pair of neutron stars collide and merge to form a new black hole. In both scenarios, an immense quantity of gamma radiation is released, followed by a fading afterglow that allows us to map the precise positions of these ancient events. Beyond the farthest quasar groups, at a redshift of 1.6, an epoch 9.5 billion years in our past, scientists discovered an astonishing aggregation of these powerful GRBs. This collection was scattered over a mind-bending expanse of 10 billion light-years. This gargantuan concentration was termed the Hercules-Corona Borealis Great Wall. While scientists consider this wall to be the largest cosmic structure ever identified, its concentration is not likely the result of an underlying superfilament of matter. GRBs are events tied to the evolution of an individual galaxy and have little relevance to the large-scale evolution of cosmic filaments. Regardless, simply attempting to comprehend a distance of 10 billion light-years is a mind-melting task. It dwarfs our human existence, our triumphs and sorrows, making them feel like a momentary breath in the boundless cosmic drama. The Hercules-Corona Borealis Great Wall transports us conceptually to a redshift of 2, a breathtaking 11.18 billion light-years from Earth. At this distance, we arrive back in the very early universe, in the midst of one of its busiest periods, the cosmic high noon. This epoch, 2.6 billion years after the Big Bang, marked the peak period of star formation. Imagine the cosmos then, a glittering expanse of young, active galaxies, veritable star factories, operating at full capacity. These nascent galaxies were grinding out the equivalent of 3,000 to 4,000 suns worth of new stars every year. Contrast this with the meager output of our mature Milky Way today, which churns out 10 suns worth of new stars per year. The early universe was a cosmic forge. These primordial galaxies would have been hives of intense, ionizing radiation. Luminous quasars continue to feature prominently, but at these depths we sometimes encounter a peculiar phenomenon. The powerful emissions from these active galactic nuclei are occasionally obscured by vast, intervening walls of gas and dust. In this case, a hot dog is not a culinary delight. It's a hot dust-obscured galaxy. Imagine a bright quasar galaxy from the earliest epochs, shining from within a thick covering of gas and dust. NASA's WISE telescope identified more than 1,000 of these hot dogs between redshifts 2 and 4. These observations allowed us to peer back in time, approaching 13 billion light-years from Earth. However, as we push beyond redshift 3, the light from these objects becomes difficult to work with. Around this distance, some models hold that the recessional velocity of these galaxies, the speed at which they are carried away by space's expansion, starts to exceed the speed of light. This does not break any laws of physics. Nothing is actually moving at faster than light speed through space. Rather, space-time itself is expanding, carrying the galaxies along. The inflation of space pushes galaxies away from each other, and at vast distances, the effective separation speed will exceed the speed of light. More than 12 billion light-years from Earth, these ancient objects are pushed away from us at such rapid rates that their faint emissions become impossibly dim and profoundly redshifted. Their light appears to stretch and slow, as their light cones are starved of photons by the universe's expansion. For a long time, the redshift bands beyond this distance were thought to be inaccessible. However, our next generation of observatories, particularly those in the infrared spectrum, are now helping to bring the vanishing light from this bygone age out of the shadows. Primordial galaxies are one of the most tantalizing targets of the James Webb Space Telescope. Among the reasons these primordial galaxies are so attractive to astronomers is their hypothesized concentrations of population 3 stars. These were the universe's first generation of stars. These colossal, short-lived titans emerged from the pristine gas, almost exclusively hydrogen and helium, left behind by the Big Bang. When these first stars began to shine, a mere few 100 million years after creation, it triggered a transformative period known as the epoch of reionization. It represents one of 2 major phase transitions for the early universe's gas. After the Big Bang, its plasma cooled enough for protons and electrons to form neutral hydrogen and helium gas. This was the Dark Age. However, as this gas coalesced to give rise to population 3 stars, their high-energy emissions began to reverse this process, reionizing the vast expanse of neutral gas. This epoch of reionization lasted for about 150 million years, concluding around redshift 6. A key question for astronomers is, was the reionization a democratic process, shared among countless galaxies? Or was it driven by a few powerful galactic oligarchs? To answer this, Astronomers are on a quest to find the farthest, oldest galaxies that ever existed. Humanity has managed to spot objects at astounding depths, peering back more than 13 billion light-years. In Ursa Major, at a redshift of 11.1, we find GNZ11. This is one of the oldest and farthest galaxies we know of, a tiny, dense pocket of nascent gas and first-generation stars. This faint smudge is thought to have taken shape only 420 million years after the Big Bang, a remarkably rapid formation. GNZ11 held the title of the farthest detected galaxy for several years. In 2022, a team at the University of Tokyo brought an even more remote galaxy into view. This newly discovered infant, termed HD1, is estimated to lie at a staggering redshift of 13.27. This means it formed a mere 330 million years after the birth of the universe. However, this distance and age await confirmation from the James Webb Space Telescope. The Webb itself recently spotted its own ultra-distant galaxy, designated Glass Z13. While not as distant in light travel time as HD1, Glass Z13 still resides in the redshift 13 band, placing it about 13.5 billion light-years from Earth. It's a challenge to comprehend such a distance, but our understanding gets wilder when we factor in the expansion of space. The 13.5 billion light-years represents how far they were when their light was emitted. The present-day versions of these galaxies reside much further away. They will have been cast away at speeds effectively faster than light. The taper distance of these galaxies today is believed to be more than 33 billion light-years. They are now so remote that their light, even if they were still shining, would never have enough time to reach our solar system. As objects fall off the grid like this, our optical view of the universe ends. This final curtain falls around redshift 20 at a light travel distance of 13.6 billion light-years, marking the era of the first population 3 stars. This ultimate limit is what scientists call the cosmic horizon. It's not a physical barrier, but a fundamental limit to what we can ever observe. Beyond this horizon could be anything. Entire civilizations could have risen and fallen in silence, utterly beyond our ken. Our journey through the observable universe concluded at the cosmic light horizon. This is the ultimate optical boundary of what we can perceive. Beyond it, light has not had sufficient time to reach the observer since the universe's birth, 13.8 billion years ago. As a result, our optical view fades into a curtain of darkness. This darkness, however, does not represent the true edge of the universe. Just beneath this optical curtain in the radio spectrum lies an older relic, the cosmic microwave background, CMB. This ancient radiation is the ghost of the Big Bang, the faintest detectable light in the universe. It is an indispensable element of modern cosmology. While older signals might exist, like the cosmic neutrino background, they are too faint for our instruments to detect. For all practical purposes, the CMB defines the edge of the observable universe. Remarkably, it provides insights into the space that extends beyond this visible horizon. This is thanks to the universe's large-scale uniformity. When viewed at its grandest scales, it appears smooth and isotropic. According to the cosmological principle, which posits the universe is homogeneous and isotropic on large scales, beyond the cosmic horizon lies more of the same. More galaxies, clusters, and voids forming the cosmic web. Without the limiting light delay, the cosmic horizon would fade away, revealing a much larger, more evolved cosmos that extends, perhaps infinitely. The earliest galaxies we've identified no longer exist in their primordial forms. In their present-day locations, they reside more than 33 billion light-years away, cast to nearly 3 times their original distance. These ancient embers would now resemble the mature galaxies we see locally, like the Milky Way and Andromeda, or even giant ellipticals like Messier 87. These evolved galaxies would dominate the unseen regions beyond our cosmic horizon. While the question of what lies beyond is straightforward, more galaxies, the more challenging question is, how much is out there? Is it merely larger or truly infinite? Answering this question requires understanding the universe's overall shape. Historically, humanity, dating back to Aristotle, believed the universe was spherical, with Earth at its center. This cosmos, they imagined, was separated from a wider plane by a physical boundary where space stops. However, mathematics has made it almost impossible to describe what would happen at such a boundary. Crucially, there is no observational evidence for such a barrier. The only exceptions are black holes, where light is trapped. Consequently, the consensus today is that the universe, regardless of its size or shape, lacks a physical edge. Instead of being enclosed in a finite sphere, the universe might be mapped to an external, perhaps infinitely stretching, surface area. Consider the Earth's surface. It is finite in area, yet without a boundary. One could travel around it indefinitely without encountering an edge. Similarly, it's now thought that the universe's collective matter and energy induce a similar effect, wrapping space around itself. The universe likely lacks edges in the traditional sense, yet it might possess curvature. This refers not to a physical bend one could see from an external vantage point, but to how space deviates from Euclidean geometry. If the universe were finite in volume, to close itself off without a boundary, it would need to curve at a large scale. Detecting such geometry could provide clues to its global shape, size, and fate. This curvature is tied to the universe's total energy density, represented by the density parameter omega. The value of omega reveals the large-scale curvature of space. Einstein's general relativity demonstrated that mass and energy curve space-time. In a universe dominated by the self-gravitation of its cosmic web, it would curve entirely around itself, closing off its finite volume like a sphere. Such a closed cosmos would exhibit positive curvature with an omega value greater than 1, omega greater than 1. 2 parallel photons would eventually converge. This universe would reach a maximum expansion, halt, and then reverse, leading to a big crunch, compressing everything back into a hot primordial state. This big crunch scenario was challenged in 1997 by the discovery that the universe's expansion has accelerated. A universe dominated by gravity cannot speed up its expansion. This observed acceleration suggests the universe is not dominated by gravity, but by a mysterious force resembling anti-gravity, which we call dark energy. Dark energy is attributed to the vacuum energy of empty space. It exerts a negative pressure, a push that inverts spacetime, where gravity would otherwise curve it inward. If most of the universe's energy is due to dark energy, space would be shaped into an open-ended, hyperbolic universe. In such a negatively curved universe, with an omega less than 1, gravity would be too weak to halt expansion, leading to a runaway expansion that continues indefinitely. Such a universe might have a saddle or horn shape. 2 parallel photons would continuously diverge as new space is created between them. Then there is the third possibility, a universe at the critical density, where omega equals 1. In such a balanced cosmos, there would be no significant global curvature. It would possess a flat geometry, mirroring Euclidean space. This flat universe would not curve itself off to form a finite volume. This is what we would expect for an infinite universe. Parallel photons would remain parallel for eternity. The forces of gravity and dark energy are perfectly balanced, preventing any global curvature. This universe would expand forever, a slow, eternal unfolding. With these three scenarios, scientists embarked on a quest to determine space's true shape. The first method involves summing the total energy densities of all its components. The second involves probing the edge of the observable universe through the cosmic microwave background, CMB. The CMB is a screenshot of the universe when it was 379,000 years old. This ancient light, when mapped, is remarkably uniform, with minor temperature fluctuations. These are the imprints of density gradients in the primordial plasma. By measuring the angular sizes between these hotspots, scientists can search for signs of gravitational lensing. By plotting triangles on this cosmic baby picture, the universe's curvature can be determined by measuring their interior angles. In a spherical, positively curved universe, the sum would be greater than 180 degrees. In a saddle-shaped, negatively curved universe, less than 180 degrees. But in an infinite flat universe, they would sum to exactly 180 degrees. Using this technique, the Boomerang probe in the late 1990s was the first to map the CMBs and isotropies. Its results concluded, with a high degree of confidence, that omega was precisely 1. This supported the suspicion that the universe might be flat. Following this, NASA's WMAP in 2001 provided more precise estimates, reaffirming that the universe is largely flat. Then, the ESA's Planck satellite in 2010 provided the most detailed dataset ever compiled, drawing the same conclusion. The universe is very near the critical density for perfect flatness. Subsequent experiments have verified this assertion. The flatness problem arises from this observation. Why is the universe so perfectly balanced? The fact that astronomers cannot discern any significant global curvature after nearly 14 billion years of evolution suggests it must have been exquisitely close to the critical density at the Big Bang. This balance remains a tantalizing mystery. There are three primary solutions proposed. First, the universe is truly flat and likely extends infinitely. Second, it is curved, but on a scale so colossal that our observable universe is just a tiny patch, making the curvature undetectable. Third, the universe has a complex, hidden topology that makes it appear flat. The idea of an infinite cosmos has profound implications. Physically, it presents a challenge. It's hard to imagine how an expanding universe that began from a small point could have reached an infinite extent in a finite time. The classical Big Bang theory tends to suggest a finite volume. Indeed, many observed properties align more closely with a finite universe. For example, on scales larger than 60 degrees in the CMB, the Planck satellite confirmed a flattening in the variability of the CMB's power spectrum. This implies a natural cutoff in wave strength, a limit to the largest possible structures, which would be improbable in a truly infinite universe. The possibility of a multiply-connected universe, such as the toroidal universe, provides an alternative explanation for the flatness problem. In this model, the universe is finite and positively curved. However, due to its peculiar topology, it appears flat. Imagine a toroidal universe, shaped like a multi-dimensional donut. Its faces would be connected, meaning if you traveled in a straight line, you would loop back to your starting point. This would allow for a finite volume without a boundary and without apparent positive curvature. CMB photons would appear to travel through flat space despite the underlying looping geometry. However, if the torus were significantly larger than our observable universe, these repeating patterns would not be detectable. A 4D hypertorus could even explain the universe's expansion and eventual contraction, leading to a cyclical universe of endless Big Bangs and Big Crunches. Another solution posits that the universe is globally curved, but on a scale so vast that this curvature is undetectable. To hide such curvature, a positively curved universe would need a diameter exceeding 20 trillion light-years. A negatively curved universe might be even larger. The challenge is reconciling such a large universe with the classical Big Bang theory's small origin. However, the smoothness and lack of topological defects in the CMB challenge the simplicity of the classical model, suggesting a preceding period of hyper-rapid expansion, which we call cosmic inflation. Cosmic inflation, a theory developed in the late 1970s by Alan Guth, offers a solution to the flatness problem. It proposes a brief but potent period of rapid expansion almost immediately after the universe's birth. This exponential expansion dramatically enlarged the nascent universe, stretching it to a size so enormous that any inherent curvature was effectively flattened out, much like inflating a balloon to the size of a planet makes its surface appear flat. Inflation explains the universe's immense size, smoothness, and lack of detectable curvature without needing complex topologies. During this period, the universe expanded exponentially, preserving its initial homogeneity while seeding the cosmos with quantum-scale density propagations. These ripples were later amplified by gravity and influenced the patterns in the CMB, becoming the seeds for all future cosmic structures. Cosmic inflation has become an accepted reality among most cosmologists. This unimaginable expansion didn't just make the universe bigger. It got bigger at a rate that defies comprehension. In the first fraction of a second, the nascent universe expanded faster than light itself. It surged from smaller than a proton to a macroscopic scale in less time than it takes light to cross that same proton. This initial expansion, cosmic inflation, is so extreme it renders every other example of growth pathetic by comparison. During this period, different regions of space were expanding away from each other at speeds exceeding the speed of light. This means information could not pass from one of these regions to another. They became causally disconnected. This phenomenon is still happening today. Right now, vast regions of space are receding from us, at speeds so immense their light will never reach us. We will never be able to observe what is happening in those causally disconnected places. As far as our observable reality is concerned, they might as well not exist. Speaking of things we can't see, let's turn to the universe's composition. What is it made of? You might suggest stars, planets, and luminous matter. Wrong. All the matter you have ever touched, seen, or interacted with represents less than 5% of the universe's total mass-energy budget. About 27% of the universe is composed of dark matter. This is a mysterious substance that does not interact with light. Its presence is known only through its gravitational effects. We have no idea what it is. And the remaining 68% is composed of something even more mysterious. Dark energy. This is the force driving the accelerating expansion of space. As for its true nature, we don't have a clue. So to summarize, we reside in a universe where 95% of everything is unknown to us. We are like ants trying to comprehend the internet. We can observe its effects, but its fundamental nature is beyond our immediate comprehension. Let us trace our understanding of gravity. Since Newton in 1687, humanity has been on a quest to comprehend it. Today, we encounter one of the biggest puzzles: dark matter. It's a mysterious substance that makes up a dominant chunk of our universe's mass. Yet, despite decades of searching, dark matter remains elusive. We have never seen or detected it. So what is it? Why can't we see it? And should we consider alternative ideas? Dark matter is a theoretical form of mass. We have never directly observed it, yet its existence is inferred with overwhelming confidence because of its gravitational effects on galaxies and clusters. Scientists theorize it might be an exotic particle that doesn't fit into our standard model of particle physics. The most puzzling aspect is that it doesn't interact with light, rendering it completely invisible. It is not dark like black, but dark as in missing mass. So, why are scientists so confident it exists? The answer lies in how galaxies behave. When we simulate the universe's formation using only visible matter, the results do not match what we observe. There is not enough visible matter to explain how galaxies and clusters hold together. Our calculations indicate that at least 85% of the mass required to bind galaxies must be dark matter. The idea that the universe contains more than visible matter isn't new, but it wasn't taken seriously until the 20th century. In the 1920s, astronomers noticed anomalies in the motions of stars in our Milky Way. The first compelling evidence emerged in 1933 from Fritz Zwicky. He was studying the Coma cluster and calculated the velocities of its galaxies, discovering they were moving too fast to be accounted for by visible matter alone. His calculations suggested there was 100 times more mass than visible, the first hint of the missing mass problem. Visible matter alone. His calculations suggested there was 100 times more mass than visible, the first hint of the missing mass problem. For decades, little progress was made, but in the 1970s, Vera Rubin and Kent Ford made a crucial discovery. They observed the rotational curves of spiral galaxies. They expected stars in the outer regions to orbit more slowly than those closer to the core, but their observations revealed the outer stars were orbiting just as fast, or even faster. This suggested a substantial amount of unseen mass extending far beyond the visible boundaries, acting as an invisible gravitational glue. Today, dark matter is a key component of our understanding of the universe. It is a cornerstone of the lambda-cold dark matter, lambda CDM model. This model describes dark matter as constituting 85% of the universe's total mass, and just under a third of all the stuff that exists. It is cold because it is hypothesized to move slowly. This property explains how the universe's large-scale structure formed. In the early universe, dark matter played a pivotal role. While normal matter was slowed by interactions with light, dark matter felt only gravity. This allowed it to clump together faster, forming an invisible scaffolding, a cosmic web of dark matter filaments. This structure still exists, serving as the gravitational highways along which luminous galaxies were born. Although we have never directly detected dark matter, we have gathered overwhelming, indirect evidence. One powerful example is the Bullet Cluster, a cosmic collision 3 billion light-years away. It is the aftermath of two smaller galaxy clusters that passed through each other. The distribution of visible galaxies and hot gas does not align with the cluster's center of gravity. The hot gas slowed down and formed a separated cloud. However, the gravitational lens reveals that the majority of the cluster's mass sailed through unimpeded. This separation suggests most of the mass is dark matter, which did not interact like the visible gas. Another powerful piece of evidence is gravitational lensing. This warping of light occurs when light from distant galaxies passes through a massive object's gravitational field. Sometimes, we observe these lensing effects in regions that appear almost empty. This gravitational shadow suggests a significant amount of unseen mass, dark matter, exerting its influence. Scientists are using various methods to directly detect dark matter. One involves searching for weakly interacting massive particles, or WIMPs. Deep underground laboratories hope to catch the fleeting interaction of WIMPs with ordinary matter. So far, these experiments have come up empty. Another method involves searching for signs of dark matter annihilation. When dark matter particles collide, they might annihilate, releasing high-energy gamma rays. While we've observed some intriguing signals, none have been definitively linked to dark matter. Given the challenges, some scientists have proposed alternative explanations. One is modified gravity, or MOND. This theory suggests our understanding of gravity might be incomplete in low-acceleration environments, like the outskirts of galaxies. According to MOND, gravity behaves differently in these conditions, which could explain galactic rotation curves without invoking dark matter. However, while MOND can explain some local observations, it struggles to account for others, particularly the bullet cluster. This is why dark matter remains the leading explanation. Despite decades of searching, the mystery of dark matter is far from solved. But scientists are not giving up. New, more sensitive observatories, like the Vera C. Rubin Observatory, are designed to shed more light on it. And perhaps the answer to the riddle of dark matter will also help us understand dark energy, the force driving the universe's accelerated expansion. In 1998, a pivotal moment in cosmology unfolded. Two teams of scientists set out to measure the universe's expansion rate. They observed distant galaxies using the Hubble Space Telescope. Based on prevailing models, they expected to find the expansion was slowing down. This deceleration would be the consequence of the collective gravitational pull of all matter. It would eventually lead to a big crunch. However, when they analyzed the light from the farthest galaxies, they made a shocking discovery. The universe's expansion wasn't just continuing, it was speeding up. This suggested the existence of a mysterious force, stronger than gravity on cosmic scales, pushing the universe apart. This was the first hint of dark energy, and its discovery is one of the biggest astronomical mysteries of the last 2 decades. Dark energy is the placeholder name for this unknown force causing the universe to expand at an accelerating rate. Unlike ordinary matter, or dark matter, dark energy has never been directly observed. Its existence is inferred from the large-scale behavior of space. There is compelling evidence that the universe has expanded more rapidly in the last 5 billion years than at any previous time. If gravity were the only dominant force, we would expect it to be slowing down. But since it is accelerating, there must be another force at work, one that acts in opposition to gravity. This force is dark energy, which exerts a negative pressure that pushes space apart. On smaller scales, within our solar system or galaxies, dark energy's effects are too weak to be noticeable. Here, gravity is dominant. However, on vast intergalactic scales, dark energy asserts its dominance. It overcomes gravity's weakening grip, causing space to expand faster over time. The volume of the universe is doubling approximately every 10 billion years. What this means for the universe's future remains one of the most profound questions in cosmology. This accelerating expansion has an unsettling implication. Galaxies we see today are relentlessly moving away from us, faster and faster. Eventually, they will recede at speeds so great their light will never reach us. The galaxies won't just disappear from view, they will disappear from causality. Events in those disconnected regions will be severed from events here. It's as if the universe is creating isolated pockets of reality. Right now, countless civilizations might be trying to contact us, but their signals are in a futile chase through expanding space. Those messages will never reach us. We exist in a shrinking bubble of observable reality, and this bubble is inexorably getting smaller. The idea of a repulsive force like dark energy isn't entirely new. It can be traced back to Albert Einstein and his 1915 general theory of relativity. When Einstein formulated his equations, he believed the universe was static. Yet his equations predicted an unstable universe that should either expand or collapse. Knowing gravity would cause it to collapse, Einstein introduced the cosmological constant. This constant was a kind of anti-gravity force he believed would keep the universe in balance. However, a decade later, when Edwin Hubble discovered the universe was expanding, Einstein abandoned his cosmological constant, calling it the greatest blunder of his life. But in a delicious irony, Einstein might have been right. The discovery of the accelerating expansion in 1998 revived the idea of a cosmological constant, this time to explain why the universe is expanding faster. The discovery that space is expanding dates to Edwin Hubble's work in the 1920s. He demonstrated that distant galaxies are moving away from us, and the more distant they are, the faster they recede. This led to the conclusion that space itself is expanding. The rate of expansion is known as the Hubble constant, measured in kilometers per second per megaparsec. Our current best estimates indicate space is expanding at about 72 kilometers per second per megaparsec. This means for every 3.2 million light-years you venture out, galaxies at that distance are moving away an additional 72 kilometers per second faster. As space expands, it affects the light traveling through it. This stretching causes the light to redshift. By measuring how much light from distant galaxies has redshifted, scientists can estimate the universe's expansion rate over cosmic timescales. To measure these redshifts, astronomers use standard candles, objects with a known intrinsic brightness. The ideal objects are type Ia supernovae, which have a remarkably consistent peak brightness, allowing precise distance calculations. By combining distance and redshift, cosmologists can calculate the expansion rate at different points in time. It was this methodology that led to the 1998 discovery. Two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, used type Ia supernova to measure the expansion rate. They expected to find the expansion was slowing down. But the results were a revolutionary surprise. It was speeding up. This led to the conclusion that dark energy must be driving this acceleration. This discovery reshaped our understanding, suggesting dark energy makes up a dominant portion of the universe's energy density and is the most powerful force on the grandest scales. Today, the most accepted model is the lambda-cold dark matter, lambda CDM model, which includes dark energy as a key component. According to this model, dark energy accounts for about 70% of the universe's energy density, dark matter another 25%, and ordinary matter the remaining 5%. Despite its importance, dark energy remains a profound mystery. One possibility, aligning with Einstein's cosmological constant, is that it's an intrinsic property of space. Another is that it's a dynamic quintessence field that evolves. There are more exotic ideas like phantom energy, which suggests dark energy could become so powerful it could tear the universe apart in a big rip. The search for dark energy's true nature continues. New experiments and telescopes are being launched to study its effects. The James Webb Space Telescope is probing the farthest reaches. gathering data to refine our understanding. The ESA's Euclid mission and NASA's Nancy Grace Roman Space Telescope will also focus on uncovering its mysteries. These missions aim to measure dark energy's equation of state, which will reveal whether its effects are constant or changing. Understanding this could allow us to forecast the universe's ultimate fate. Galaxies are the ultimate star cities. Most are packed with hundreds of billions of stars, each a sun. These stars often have their own planetary systems. All of this is held together by the supermassive black holes at their centers. Recent estimates suggest up to 2 trillion galaxies within the observable universe. We reside in the Milky Way. However, there are countless larger and older galaxies that make our own appear small. Galaxies can be massive, but what is the largest galaxy in the entire Tran universe? One contender is IC 1101. IC 1101 holds the unofficial title as the largest and most massive galaxy ever discovered. This ancient elliptical galaxy is so large, it could engulf our Milky Way dozens of times over. Its estimated star count has sparked discussions about the possibility of life beyond Earth. Adding to its awe is the hypothesized ultramassive black hole at its core, a gravitational engine of unimaginable power. IC 1101 is 1.04 billion light-years from Earth in the constellation Virgo. Despite its distance, it shines with an apparent magnitude of 14.73, a testament to its colossal stellar population. Our Milky Way is about 100,000 to 120,000 light-years in diameter. IC 1101 stretches across 6 million light-years. That makes it 2,000 times more massive than our galaxy. Its estimated 100 trillion stars dwarf the Milky Way, rendering our home a humble footnote. 100 trillion stars, more than the cells in your body. Given its density of stars, it likely has few of the diffuse nebulae that characterize younger, star-forming galaxies. Based on its size and reddish color, astronomers believe IC 1101 is in the later stages of its life. Most of its stars are older and rich in metals, estimated to be 7 to 8 billion years older than our Sun. This suggests the primordial seeds that grew into this behemoth were sown not long after the Big Bang, making the galaxy about 11 billion years old. The sheer number of stars in IC 1101 has ignited speculation about intelligent life. Mathematically, this galaxy would have the highest theoretical probability of hosting life. However, the intense radiation and proximity of stars in its dense core might make conditions less favorable for complex life than in less crowded spiral galaxies. One poetic idea is that civilizations in IC 1101's core might not be able to perceive other galaxies. The galaxy's core is so packed with stars and starlight that it might obscure the view of the universe beyond, leading its inhabitants to see IC 1101 as the entirety of existence. IC 1101 was first noted in 1790 by William Herschel as a faint smudge. It took over a century before it was officially catalogued in 1895 by John Louis Emile Dreyer. At that time, astronomers had no idea of its colossal size. It wasn't until 1995, with the Hubble Deep Field images, that humanity began to comprehend how vast this galaxy is. Why is IC 1101 so massive? The answer lies in galaxy formation and mergers. Galaxies are thought to have formed from primordial gas clouds collapsing under their own gravity. These nascent galaxies then engaged in a continuous process of collision and merger over billions of years. This cosmic cannibalism led to progressively larger structures. Dwarf galaxies collided to create spiral galaxies like our Milky Way. These spirals then merged to form even larger ellipticals. IC 1101 is a quintessential giant elliptical galaxy formed from countless mergers. It is now likely in the final stages of its life, its star formation rate having long since peaked, its stellar population aging, and its immense black hole consuming whatever remains. Given its size, IC 1101 is expected to harbor an ultramassive black hole. This gravitational leviathan is possibly one of the largest ever discovered. The precise size remains a mystery, with estimates ranging from 40 to 100 billion times the mass of our Sun. While some models suggest a physical size limit for black holes around 50 to 60 billion solar masses, IC 1101's black hole challenges these ideas, making it a topic of ongoing research. As we continue to explore the universe, IC 1101 stands as a testament to the cosmos's incredible scale and complexity. And while it currently holds the title as the largest galaxy, it's possible even larger galaxies exist beyond our field of view. Let's turn to another celestial colossus. In 2011, a team using the South Pole Telescope discovered more than 24 distant galaxy clusters. 12 had never been seen before. Among them was the Phoenix Cluster, a massive group of about 1,000 galaxies emitting intense radiation. Even within this cosmic city, its brightest member radiated with extraordinary brilliance. Over the next decade, the Phoenix Cluster became one of the most studied galaxy clusters. It broke records for its high X-ray emissions, the amount of hot gas it contained, and its rapid star formation. But recently, it has garnered more attention. Nestled in the heart of its central galaxy lies what might be the largest black hole ever discovered. This gravitational monster is so massive, it could dwarf entire galaxies. But why do some astrophysicists believe this black hole is the biggest? Who are they, and what evidence led them to such a conclusion? How large can black holes get? And if this one isn't the largest, which one is? These are the questions we will now explore. Black holes are not holes in space, but incredibly dense, warped regions of spacetime. Within them, gravity becomes so strong that nothing, not even light, can escape its pull. This creates an invisible boundary, a point of no return, called the event horizon. The basic idea is simple. Compress enough mass into a small enough space, and a black hole will form. One of the most common ways a black hole forms is through the gravitational collapse of massive stars. When a giant star exhausts its nuclear fuel, it undergoes a violent collapse. Its outer layers are blasted away in a supernova. What remains is a dense core. If this core is heavy enough, more than a few times the mass of our Sun, it will continue to collapse until it forms a stellar black hole. These are the smallest and most common type, ranging from a few to a few dozen solar masses. Our Milky Way might contain millions of them. While most are invisible, some become visible when they feed on surrounding gas and dust. This feeding process is accretion. It's how black holes grow. Matter from their surroundings gets pulled inward, forming a swirling, hot accretion disk. Some of this matter spirals across the event horizon, adding to the black hole's mass. The rest orbits at incredible speeds, superheated, and radiating intense energy. Over millions of years, a stellar black hole might grow to over 100 solar masses, at which point it would be classified as an intermediate mass black hole, a rarer category. Intermediate mass black holes can grow to tens of thousands of solar masses. They are often found at the centers of dense star clusters or remnants of protogalaxies. But how do they grow so large? Accretion alone cannot account for their scale. Scientists theorize that more dramatic processes, like black hole mergers, must be at play. When two black holes collide and merge, they form a larger black hole. This process allows black holes to grow rapidly, especially in the early universe or when galaxies collide and their central black holes merge. At the centers of most galaxies, we find supermassive black holes with masses greater than 100,000 suns. In large galaxies like our Milky Way or Andromeda, these can reach millions of solar masses, an event horizon large enough to swallow entire stars. These supermassive black holes play a crucial role in shaping their host galaxies. Their gravity can trigger or quench star formation. It's a consistent pattern. Galaxies with massive central bulges have equally massive black holes at their cores. This is why IC 1101, with its gargantuan nucleus, has long been a candidate for housing the largest black hole. The search for the largest black hole is an ongoing quest. IC 1101 was a strong contender. The black hole at its center is believed to have a mass of around 40 billion suns, with an event horizon so vast it would encompass our solar system many times over. For black holes of this scale, the term supermassive isn't enough. For those exceeding 10 billion suns, astronomers use terms like ultramassive black holes or stupendously large black holes, SLABs. Many of the largest SLABs cluster around the 40 billion solar mass mark. It's not clear if black holes larger than 50 or 60 billion suns can exist, as their accretion disks might become unstable. However, there is always an outlier. TON 618, a powerful quasar, is fueled by a black hole with an estimated mass of 66 billion suns. Discovered in the 1970s, its event horizon would stretch across nearly 400 billion kilometers. That's more than 40 times the distance between our Sun and Neptune. Despite this staggering estimate, TON 618's mass has been revised closer to the 40 billion solar mass mark. Yet, for many reasons, it remains a favorite among astronomers. Recently, a new contender has emerged, the black hole at the heart of the Phoenix Cluster. Located 5.8 billion light-years away, the Phoenix Cluster was discovered in 2011. Its central galaxy, Phoenix A, is churning out new stars hundreds of times faster than our Milky Way. This star formation is fueled by rapidly cooling gas. But what is captivating is the possibility that the black hole at Phoenix A's center could be the largest ever discovered. In 2015, a team proposed it might have a mass of 100 billion suns, a figure that doubles the theoretical limit for black hole growth. If this estimate is true, Phoenix A's black hole would be an undisputed giant, with an event horizon stretching over 500 billion kilometers. However, this estimate is based on indirect evidence. Other studies suggest it might be closer to other ultramassive black holes in the 40 to 60 billion solar mass range. The true scale remains a subject of debate. The search for the largest black hole continues. While the idea of a 100 billion solar mass black hole is exciting, it's more likely that Phoenix A's black hole, while ultramassive, is not that large. We don't yet have a reliable way to measure its mass, but as new techniques develop, we may soon have a more definitive estimate. In the interim, the quest continues. Whether the ultimate title belongs to TON 618, the Phoenix A black hole, or another giant, the mysteries of these behemoths remain one of the most fascinating areas of astronomy. For now, TON 618 still holds the unofficial title. What is the biggest black hole in the universe? While new contenders emerge, TON 618 remains a top contender, if not the biggest. We still don't know all the details, but what we do know is mind-blowing. This hyperluminous quasar was once mistaken for an ordinary star, a testament to its power to mimic nearby objects from unimaginable distances. It is a primordial leviathan calling out to us from over 10 billion light-years away. But is it the unchallengeable behemoth we believe it to be? With many of its properties pushing the limits of our understanding, Ton 618 might have more surprises in store. Until we uncover those truths, we are left to contemplate this monster as possibly the largest black hole in the known universe. Ton 618 is located at the heart of a distant galaxy 10.37 billion light-years away in the constellation Canes Venatici. Despite this distance, it shines with an absolute visual magnitude of -30.7. This means its intrinsic brightness is equivalent to 140 trillion suns, making it one of the brightest objects in the universe. In quasars, brightness correlates with the mass of the central black hole. For Ton 618, this implies a mass of 66 billion times that of our Sun. For comparison, the black hole at our Milky Way center is only 4.3 million solar masses. Ton 618 is thousands of times more massive. Using our understanding of black hole physics, scientists estimate Ton 618's event horizon has a radius of about 194 billion kilometers. This is so enormous it dwarfs our entire solar system. Our solar system to the Kuiper Belt's edge has a diameter of just under 300 billion kilometers. Ton 618's event horizon is larger than our solar system. But how can a black hole reach such a massive state if the light we are observing from it started its journey billions of years ago when the universe was significantly younger? The light from Ton 618 tells us it existed when the universe was only 1 to 2 billion years old. This implies it was already a colossal leviathan when the universe was incredibly young. There's no way to measure how much more it has grown since. However, physicists have proposed theories to explain its rapid growth. The leading idea is that it might be a direct collapse black hole. Unlike most black holes, which form from a single dying star, a direct collapse black hole forms from the rapid collapse of an entire supermassive gas cloud. This top-down process, occurring in the early universe, could also involve swallowing thousands of nascent stars within that cloud. This would provide an efficient pathway for rapidly building a massive black hole, explaining Ton 618's size at such a young cosmic age. While these measurements might be refined, for now, they are our best estimates. But how was Ton 618 discovered? The initial observation was in 1957. It was noted in a survey of faint blue stars, mistakenly categorized as one. Its true nature remained hidden until the 1960s, when astronomers noticed powerful radio sources from seemingly stellar objects. They began to realize these stars were something much more distant and powerful: quasars. The pivotal discovery came from Martin Schmidt in 1963. He analyzed the spectral lines of these quasars and found they indicated immense redshifts. These redshifts demonstrated the objects were incredibly far away, and the light we received was billions of years old. Ton 618 was revealed to be a powerful quasar, fueled by one of the most massive black holes ever discovered. Calculations based on its luminosity showed its black hole must have a mass of at least 66 billion suns, with an event horizon radius of over 1,300 astronomical units, AU. Despite these figures, mysteries surround Ton 618. We can't see the galaxy that surrounds it. Its luminosity outshines its home. Some scientists have raised doubts about its true nature. The fact it was so massive so early adds to the enigma. While quasars were more common in the early universe, most black holes of this size should have faded by now. Yet, Ton 618 stands out as a brilliant anomaly. Some researchers suggest a theoretical size limit for black holes, perhaps around 50 billion solar masses. Beyond this, a black hole might lose its accretion disk and stop growing. But Ton 618 seems to defy this limit. Why haven't we found others of this size in the same region? And what unique conditions made Ton 618 such an outlier? We don't have all the answers, but Ton 618 continues to captivate scientists. It's possible our understanding of black holes is incomplete, and Ton 618 is showing us how much more we have to learn. For now, it holds the title as the largest known black hole. One of the most enduring mysteries is not just what black holes are, but what happens inside from them. We know anything crossing the event horizon is torn apart and lost to our universe. But what if you could venture inside, to its core? What might you find? This question has puzzled scientists and mystics for over a century. Black holes are some of the most enigmatic objects, defying the laws of nature as we understand them. While what happens inside a black hole is a theoretical mystery, one idea captures the imagination, that black holes might be gateways to other parts of our universe, or even to new universes altogether. Let's explore what could lie on the other side. To grasp how a black hole might be a gateway, we must understand the nature of space and time. No one understood this better than Albert Einstein. His theory of general relativity reveals that time and space are intertwined, forming a flexible fabric called space-time. Imagine space-time as a trampoline. The presence of mass causes this fabric to warp. The heavier the object, the more space-time bends. This bending is what we perceive as gravity. Now, if you take a massive object and compress it into a tiny space, space-time's curvature becomes so extreme it creates a black hole. Gravity is so strong it pulls everything inward, including light. This leads to the event horizon, a point of no return. At the center lies the singularity, a point where all mass is infinitely compressed and the laws of physics break down. But here's where the narrative takes a speculative turn. Some scientists suggest this extreme warping of space-time might do more than create a black hole. What if, instead of culminating in a singularity, it pinches space-time to create a tunnel or bridge, connecting it to another part of our universe or a new one? This concept is a wormhole. Imagine space-time as a flat sheet of paper with two dots far apart. To travel between them, you would traverse the distance across the sheet. But if you fold the paper so the dots touch, you create a shortcut. That's what a wormhole could be, a shortcut through space-time. Wormholes are a staple of science fiction, but they are also grounded in the mathematics of Einstein's general relativity. In theory, a black hole's gravity could bend space-time enough to form this bridge, an Einstein-Rosen bridge. However, even if wormholes exist, they might not be practical for travel. They could be incredibly unstable, forming and collapsing almost immediately. And the intense gravity and tidal forces would likely crush anything attempting to pass through. If black holes pull everything in, is there an opposing entity, something that spews matter and energy out? This is where the concept of a white hole enters. A white hole is the reverse of a black hole. It would explosively expel matter and energy, defying attempts to enter it. In theory, if a black hole were connected to a white hole through a wormhole, whatever falls into the black hole could be ejected from the white hole into another part of space or a new universe. But there's a catch. White holes would be incredibly brief and unstable, collapsing back into black holes themselves. Are white holes real? While the concept is intriguing, they have remained purely theoretical. We have never observed one. Their existence is a mathematical possibility, not a confirmed reality. The framework for white holes stems from the mathematics of black holes, specifically the Schwarzschild metric, which describes a symmetrical, eternal black hole in an empty universe. When the time reversal symmetry is applied, it suggests the existence of white holes. However, this mathematical extension doesn't guarantee they exist in our complex universe. While wormholes and white holes might seem far-fetched, there is one scenario where black holes could play a more fundamental role: the birth of new universes. Some theories suggest that when matter falls into a black hole and is compressed into the singularity, it might bounce back, creating a new universe on the other side. In this view, black holes might be the primordial seeds of new universes, miniature cosmic wombs, each leading to a big bang in another reality. This leads to the concept of black hole cosmology. It proposes our universe might be one of an infinite multitude, each born from a black hole in a parent universe. It's a wild idea, but if true, it could explain some of our universe's biggest mysteries. For instance, it could explain why our universe started in a state of extreme density and how it evolved from that state. It paints a picture of a constantly self-generating cosmos. Even if wormholes and white holes don't exist as we imagine, there is another possibility for the fate of black holes. What if a black hole eventually becomes a white hole at the end of its life? Thanks to Stephen Hawking, we know black holes slowly lose mass through Hawking radiation. As they radiate, they shrink. In the unimaginably distant future, they could become so small and hot that they undergo a final explosion, releasing their remaining energy in a flash, reminiscent of a white hole. In that distant future, after all the stars have burned out, these dying black holes could be the last sources of light in a cold, dark universe. They might not create new universes or open wormholes, but they could still play a final, profound role. The truth is, we still don't fully comprehend black holes. They remain one of the most mysterious phenomena. Whether they lead to new universes, serve as gateways, or are ultimate prisons, they challenge our understanding of reality. As we continue to study them, who knows what discoveries await? Let us turn to the most profound questions of all. What is the origin of everything? How did reality come to be as it is? These questions may seem unanswerable, yet humanity has made astonishing strides in finding scientifically grounded answers. The universe is unimaginably old and vast, but it has not always been this way. By tracing its history backward, one can reach its earliest moments, a time when the entire universe was smaller than the tip of a needle. Human beings are not separate from this cosmic narrative. We are made from the elements forged in the hearts of ancient stars, synthesized from the hydrogen and helium present at the beginning of time. The saying, "From dust you came and to dust you will return," holds profound scientific truth. Life is a product of the arrangements of atoms, refined through evolution. In a sense, we are the universe becoming aware of itself. The epic story of our origins is written across the night sky, in the light of distant galaxies, in the elements that compose our bodies. As we enter an age of unprecedented technology, we are beginning to understand that story like never before. Our most comprehensive model for the universe's origin is Big Bang cosmology. This framework posits the universe began at a specific point in time, not in a void, but as an expansion of space itself, and has been expanding ever since. While it remains the prevailing model, other speculative models exist. By rewinding the cosmic clock, we arrive at a moment 13.8 billion years ago. At this instant, the universe was infinitesimally small, unimaginably hot, and impossibly dense, a state of pure energy, a singularity where all known laws of physics break down. The universe's initial size was effectively zero. Then, something occurred. We don't know what triggered it, but something caused this point to expand rapidly, allowing its contents to begin their cosmic journey. As the universe expanded, its temperature and energy density, initially infinite, began to decrease. As the energy diffused and the temperature dropped, conditions became conducive for the formation of the first structures. There was no literal bang at the Big Bang. The universe began as a state of immense heat and has continuously cooled and expanded, The term Big Bang is a metaphorical description of the early seconds of the universe's existence, when it was unimaginably hot, dense, and undergoing rapid expansion. Crucially, the universe's expansion was not like a sphere expanding century in time something. The very metric of space-time changed and evolved. This makes it difficult for our models to describe the universe's first moments. There is no discernible center to this expansion. The Big Bang happened everywhere, all at once, in every point of nascent space. Today we perceive four fundamental forces: gravity, the strong nuclear interaction, the weak nuclear interaction, and electromagnetism. However, during the earliest fraction of time, the Planck epoch, up to 10 to the power of minus 43 seconds after the Big Bang, these forces are theorized to have been unified into a single superforce. This unified force is beyond our ability to test, yet a consensus of scientists agrees it likely existed. In this extreme state, the laws of physics as we know them may not have applied. The universe was a tiny, hot, chaotic mesh of pure energy. A fraction of a nanosecond later, as the universe expanded and cooled, this unified force began to separate into the individual forces we observe today. This process, known as symmetry breaking, caused the primordial force to divide. Gravity was the first to emerge, followed by the electroweak interaction. As temperatures fell below 10 to the power of 28 Kelvin, the electroweak force split into the strong nuclear and electromagnetic interactions. This sequence established the four fundamental forces that govern all matter and energy today. Following this, the universe underwent cosmic inflation. In under a trillionth of a second, from 10 to the power of minus 36 to 10 to the power of minus 32 seconds after the Big Bang, the nascent universe expanded exponentially, becoming at least 10 to the power of 78 times more voluminous. This expansion did not violate relativity because it was space-time itself expanding, not objects moving through space. This inflationary period laid the groundwork for the universe's large-scale structure, distributing its contents with remarkable uniformity. As the universe, now vastly expanded and cooler, continued its march through time, the energy that powered inflation decayed, spontaneously transforming into the first elementary particles, the building blocks of the universe. The hot, dense quark-gluon plasma that emerged from this cooling process led to the formation of the first atomic nuclei. As the cosmos continued to cool, quarks combined to form hadrons, such as protons and neutrons. Within the first second of cosmic time, the universe had established its fundamental laws and begun to bind elementary particles. As it continued to cool, the density of photons decreased, and matter began to dominate the universe's gravitational behavior. The universe transitioned from a radiation-dominated to a matter-dominated era. In this transition, dark matter played a critical role, forming the first gravitational wells. Around 377,000 years after the Big Bang, the universe had cooled sufficiently for electrons to combine with protons and neutrons to form the first stable, neutral atoms. This process, recombination, allowed photons to travel freely for the first time. This decoupling of light from matter led to the release of the cosmic microwave background, CMB, the oldest light in the universe we can still detect. The CMB years after the Big Bang, the universe had cooled sufficiently for electrons to combine with protons and neutrons to form the first stable, neutral atoms. This process, recombination, allowed photons to travel freely for the first time. This decoupling of light from matter led to the release of the cosmic microwave background, CMB, the oldest light in the universe we can still detect. The CMB provides a snapshot of the universe at this early stage, revealing tiny temperature fluctuations that were the seeds for all future cosmic structure. As the universe continued its expansion, it entered the Dark Age. For millions of years, it was devoid of light-emitting sources. However, under gravity's influence, vast clouds of hydrogen and helium began to coalesce, eventually leading to the formation of the first stars. These were the population 3 stars, colossal giants that emerged about 300 million years after the Big Bang. They began to illuminate the universe, ending the Dark Age and beginning the stelliferous era, the era of stars. As these first stars exploded in supernovae, they enriched the surrounding gas clouds with the first heavy elements, carbon, oxygen, iron, essential for planets and life. This cycle of stellar birth and death led to the formation of more complex stars and, eventually, the first galaxies. By 800 million years after the Big Bang, these early galaxies were merging and forming the majestic spiral structures we see today, often bound by their central supermassive black holes. The first quasars lit up the nascent universe, their light offering a window into that energetic epoch. Over the subsequent few billion years, galaxies clustered together, forming ever larger structures. These aggregations arranged themselves along the filaments of dark matter, forming the monumental cosmic web. One such structure is the Laniakea Supercluster, within which our Milky Way formed about 8 billion years ago. And within our Milky Way, our Sun came into being, along with Earth. On Earth, life emerged, eventually leading to humanity, a species capable of contemplating its own origins. Despite our remarkable understanding, there is still so much we don't know. We have a solid grasp of asterisk, how the universe evolved, but we know little about asterisk, why it began. Understanding the reasons behind its origin could provide insight into its ultimate destiny. The cosmos we inhabit today has not always been this way, and it will not last forever. Its story is still being written. The wonders of our observable universe might be only a fraction of the ultimate story. Are we part of a multiverse? This profound question leads to the contemplation of a parallel universe, the idea that our cosmos is not singular, but part of something infinitely larger, a meta-reality known as the multiverse. While often dismissed as speculative, the multiverse hypothesis, in its myriad interpretations, offers a vast landscape of possibilities. Some interpretations suggest effects that could have observable impacts on our own universe. The idea forces us to consider our existence in the grandest context imaginable. However, the fantastical version of the multiverse popularized in entertainment is not rooted in scientific realism. Mainstream cosmologists approach the topic with caution due to the lack of direct observational evidence. Yet, there are many forms a multiverse might take. Some scientifically grounded interpretations emerge logically from existing evidence in our own universe. One of the simplest interpretations is the quilted cosmos. This idea posits that we exist within an infinite universe. If the universe is infinite, then by the nature of infinity, anything that can happen will happen an infinite number of times. There would be an infinite number of Hubble volumes identical to our own. This would allow for every conceivable event to play out infinitely often. Because there are only a finite number of ways atoms can arrange themselves in a finite volume, we would expect to see repeating patterns, including potentially exact copies of ourselves. This model suggests an endless number of parallel observable universes, all governed by the same fundamental laws of physics. According to Max Tegmark, this would be a level 1 multiverse. In this scenario, galaxies continue indefinitely in an infinite spatial expanse. Such a reality would make it almost impossible that we are the only intelligent civilization. While the cosmic horizon might suggest a finite universe, the observed flatness of the cosmos hints at the possibility of an infinite one. While the idea of an infinite universe is intriguing, cosmologists typically don't rely solely on its observed flatness. Instead, they turn to the theory of cosmic inflation. As discussed, this theory posits a brief, intense period of exponential expansion shortly after the universe's inception. During this epoch, the primordial contents were stretched and smoothed, preserving its flat density and preventing the development of mass density gradients. Cosmic inflation, proposed by Alan Guth, has become an indispensable part of the standard model of cosmology. It was initially conceived to resolve issues with the classical Big Bang model, but gained support with the discovery of dark energy. However, Guth and others began to explore a more radical idea. What if cosmic inflation didn't end uniformly across all of space? This led to the concept of eternal inflation. In this scenario, the inflationary field continues indefinitely in vast regions, continuously spawning new, quote, bubble universes. Eternal inflation gives rise to a level 2 multiverse. This is a diverse landscape populated by countless hot bubble universes, each a distinct cosmos, scattered across an infinitely expanding higher dimensional expanse. In this model, new bubbles are continuously breaking off from the inflationary field. Each new bubble universe is potentially governed by entirely different laws of physics. Unlike the level 1 multiverse, the bubble universes of a level 2 multiverse may possess unique preconditions, leading to an array of different fundamental forces, particles, and physical constants. This variation results in a meta-reality with far more diversity. It could range from universes similar to our own to chaotic, starless voids, or even universes with different numbers of dimensions. The Level 2 multiverse presents a rich landscape where regions with varying laws of physics coexist, a more diverse interpretation of parallel universes. Another intriguing interpretation within the Level 2 multiverse framework is the cyclical universe. This idea posits that our cosmos is one iteration in an eternal cycle of universes being born, expanding, contracting, and repeating the cycle. This concept was formalized by Alexander Friedman in 1922. His models suggested a dance, a Big Bang, expansion, and eventual contraction into a big crunch, only to rebound and start again. Although this model faced challenges with the discovery of accelerating expansion and increasing entropy, alternative cyclical models have been proposed. Sir Roger Penrose's conformal cyclic cosmology suggests our Big Bang was the final event of a previous universe, an eon, that expanded, cooled, and reached a state of infinite dilution, becoming indistinguishable from a new Big Bang. Penrose theorizes that signatures like remnants of ultramassive black holes could carry over from one universe to the next, providing a connection across cycles. Alternatively, the universe might be one of many in a vast population, linked in a family tree-like hierarchy, ruled by a process akin to natural selection. This is the Feckin universe theory proposed by Lee Smolin in 1992. It suggests new universes are born from black holes. Each time a black hole forms, it could trigger the creation of a new cosmos on the other side. Each new cosmos would inherit and slightly modify the physical laws of its parent. Over eons, this process would favor universes capable of efficiently producing black holes. In this Level 2 multiverse, the ultimate extent of reality could be an infinite aggregation of interlinked universes, a sprawling family tree. Each universe would evolve through a process akin to natural selection. This family tree might be infinite, Or it could form a colossal, self-contained closed-loop system where the cosmos eventually creates itself in an eternal repetition. Moving to theoretical physics, string theory offers another interpretation of a level 2 multiverse. It posits that the fundamental building blocks of reality are tiny, vibrating strings. These strings exist in multiple hidden extra dimensions. These dimensions could give rise to a multitude of brane universes, each a distinct four-dimensional reality embedded in a higher dimensional space called the bulk. Each brane universe would have its own configuration of extra dimensions and, consequently, its own physical properties. In the string theory landscape, there could be a staggering number of potential universes, perhaps 10 to the power of 500 distinct possibilities. Each would correspond to a different way the extra dimensions are configured. One model is the ekpyrotic model, which proposes our universe was created by a collision between two parallel branes. Similar collisions could lead to the continuous creation of other universes. Shifting to quantum theory, we encounter the level 3 multiverse. This is based on the many worlds interpretation, MWI, of quantum mechanics. Proposed by Hugh Everett III in 1957, it suggests every possible outcome of a quantum event plays out in its own separate universe. The universe constantly splits into multiple parallel realities, each following a different timeline. The level 3 multiverse visualizes reality as an infinitely branching tree. At every decision point, the universe divides. Every choice you make gives rise to a new universe where the alternate outcome is reality. While controversial, it provides a framework for understanding the infinite possibilities in the quantum realm. It suggests every probabilistic outcome is a realized reality somewhere. Finally, we arrive at the most expansive interpretation, the level 4 multiverse, the mathematical multiverse. This is the complete collection of all conceivable realities. Every mathematically consistent universe, every possible set of equations, exists somewhere across an infinitely vast plane of pure mathematical possibility. The level 4 multiverse encompasses every single possibility. This interpretation demands we take mathematics as the literal coding language of the cosmos. It suggests reality mathematical. It also opens the door to the simulation hypothesis, which posits our universe could be a simulated reality, a computer program run by a higher dimensional species, perhaps beings within a level 3 multiverse themselves. The simulation hypothesis is a compelling application of the level 4 multiverse. It posits that all technologically advanced civilizations will eventually develop the ability to simulate entire universes. These simulations would be complete with physical laws, cosmic histories, and conscious, self-aware beings who would be unaware they are in a program. If this is feasible, it raises a profound possibility. Our entire existence is a simulation. We could be part of a nested hierarchy of simulated realities, digital beings in a digital cosmos. While speculative and untestable, it offers a chilling perspective on reality. However, some scientists argue the finely tuned properties of our universe can be explained more simply by the anthropic principle. This states the universe must possess the properties necessary for conscious life to exist, because if it didn't, we wouldn't be here to observe it. Despite the speculative ideas surrounding the multiverse, there are profound gaps in our understanding of our own universe. If humanity can develop a theory of everything, reconciling quantum mechanics with general relativity, it may provide the key to unraveling the multiverse's deepest mysteries and finally answering the question, how big is the universe? What if our entire universe is merely part of something even more vast? This leads us to the holographic principle. This counterintuitive idea emerged from attempts to unify quantum mechanics and gravity. It suggests all the information in a volume of space can be encoded on its boundary, a surface of lower dimension. Think of a hologram on a credit card. It contains a three-dimensional image, but the information is stored on a two-dimensional surface. If the holographic principle is correct, our three-dimensional reality might be a projection from information encoded on a two-dimensional surface at the universe's edge. Everything you've ever experienced might be shadows cast by patterns of information existing in fewer dimensions. But the bizarre doesn't end there. Some theories suggest our universe is a vibrating membrane, a brain, floating in a higher dimensional space, the bulk. These membranes could collide, generating energy and triggering new Big Bangs, spawning new universes. Our reality might be the result of a cosmic fender bender in dimensions we can't perceive. Other models propose we are living inside times a black hole in a higher dimensional universe. From our internal perspective, we see an expanding cosmos. But from an external vantage point, we might be information falling into a black hole. Then there's the simulation hypothesis. It suggests our universe is a sophisticated computer program run by an ancient civilization. If computational power continues to grow, future civilizations might simulate universes. These simulations would be populated by conscious beings unaware of their nature. Statistically, if this is possible, the number of simulated universes would vastly outnumber the single base reality, making it more likely we are in a simulation. Every star, every galaxy might be intricate code running on a cosmic computer. The disturbing part is there's no known way to prove we are not 24 in a simulation. But whether we are real or simulated, the scale of the possibilities remains undiminished. Even if our universe is a simulation, something had to create the computer running it. That something would exist in a reality even more vast and complex. This creates an infinite regression of possibilities. Perhaps we are simulations on computers that are themselves simulations, in an endless chain of nested realities. Perhaps reality is a fractal hierarchy of nested simulations, extending infinitely upwards and downwards. This fractal nature might extend to the universe's physical structure. As noted earlier, the large-scale structure of the universe, the cosmic web, bears an uncanny resemblance to neural networks in biological brains. What if this similarity isn't a coincidence? What if consciousness and cosmic structure are manifestations of the same underlying principles on different scales? Perhaps every conscious being is a tiny universe. And perhaps every universe is a vast, conscious being. Perhaps the thoughts in your head are like galaxies forming in a microscopic cosmos. And perhaps our cosmic web is a fleeting thought in a vast, cosmic mind. If so, the question how big is the universe becomes meaningless. Size becomes relative. What matters are the intricate patterns that repeat at every level of existence. And those patterns might be infinite. This infinite complexity might be why reality appears so fine-tuned for the emergence of consciousness. It's not that the physical constants were adjusted for life. Rather, consciousness is an inevitable emergent property in any sufficiently complex system. We exist because the universe is so vast and rich in potential that every conceivable form of organization, including consciousness, must eventually emerge. Consciousness is not a rare phenomenon, but the natural result of matter and energy interacting over immense cosmic scales. But even this perspective might be missing something more fundamental. What if size itself is an illusion? What if space, time, matter, and energy are all emergent ways of describing something more primordial that does not possess extension or duration? Some theories in quantum gravity suggest space-time itself is not fundamental. Instead, it emerges from more basic structures that exist outside our concepts of size and scale. These constituents might be purely mathematical, pure information, or something so alien we have no words for it. In this view, asking, "How big is the universe?" would be like asking, "How heavy is the color blue?" The question assumes categories that don't apply to reality's fundamental nature. Perhaps the universe is not big or small. Perhaps it simply coincides. When we contemplate these cosmic scales, we are like characters in a video game trying to understand the computer running their world. The computer doesn't exist within the game space. It doesn't have a size comparable to objects in the game. It is a different category of existence. If our universe is like that, all our measurements might be missing the point. We might be trying to understand something infinite and dimensionless using tools designed for a finite dimensional reality. But here lies a beautiful paradox. Even if we can never fully comprehend reality's ultimate nature, the act of trying changes us. When you contemplate an infinite universe, something infinite awakens within your consciousness. When you consider that reality might be mysterious, you grow comfortable with mystery. When you realize your fleeting existence is both infinitely small and infinitely significant, you transcend normal categories. You become more expansive, capable of holding contradictions. Perhaps that transformation is the point. Perhaps the universe is incomprehensibly big to expand our consciousness, to force us to grow beyond our limitations, to evolve into beings capable of contemplating infinity and finding joy in it. Here's the final twist. You are not observing the universe from the outside. You are participating in its evolution from the inside. Every time you contemplate cosmic scale, you add something new to the universe. You are not just matter contemplating matter. You are the universe becoming more conscious of itself. If consciousness is fundamental, your thoughts about cosmic scale might be actively shaping it. Your awareness of infinity might be helping to create infinity. In contemplating how big the universe is, you are participating in the universe's ongoing project of understanding and creating itself. You are both the question and the answer. And that paradox might be the most profound description of what it means to exist. But let's pull back from this theorizing and confront something that might make your skin tingle. We've been conversing about infinite space and eternal time as if they were just big numbers. But infinity is not a number. It breaks the foundations of mathematics. When mathematicians grappled with infinity, they found it behaves in ways that violate our intuition. If you have an infinite set and remove half, you are left with infinity. If you double an infinite set, it remains the same size. This has an unsettling implication for an infinite universe. Every event that can happen doesn't just happen once. It happens infinitely many times. Right now, infinite versions of you are reading these words. But there are also infinite versions who stopped reading at the beginning, and infinite versions who do not exist at all. In an infinite universe, every conceivable variation occurs infinitely often. This logic implies there are infinite universes where the laws of physics are different, but also infinite universes where the laws are the same, yet produce impossible results. There are regions where your exact atomic configuration exists, but the impossible is routine. Objects might fall upward, time might run backward. If space is infinite, then somewhere there exists a replica of Earth where gravity repels. Our physics should render this impossible. But in an infinite universe, impossibility is just another event that must occur somewhere, infinitely often. This leads to the measure problem. If every possible event happens infinitely often, how do you calculate probabilities? How do you determine what is normal versus rare? Traditional logic breaks down. In an infinite universe, your existence is both incredibly common and incredibly rare. There are infinite copies of you, making you statistically mundane. Yet, there are also infinite copies of every other possible person, making your specific configuration vanishingly unlikely. This becomes more unsettling if the universe is infinite in time. This would imply no singular beginning, no Big Bang. The universe has always existed, without beginning or end. Every event in its history has already happened an infinite number of times, and will happen an infinite number of times again. Your birth, this moment, all of it has already played out countless times. You have lived this life before, an infinite number of times, in an infinite number of variations. This concept of eternal recurrence challenges our sense of uniqueness. Nothing you do is truly unprecedented. Every word you speak has been spoken before. Every thought you think has been thought. But the flip side is, nothing you do is meaningless. Every action happens an infinite number of times, creating infinite consequences. Your choices matter infinitely because they are made and remade an infinite number of times. You are both the most insignificant speck and the most important being. This paradox extends to consciousness. In an infinite universe, every possible configuration of matter occurs, including configurations identical to your brain. There are infinite copies of your consciousness, but are they really separate copies? Or are they all the same consciousness, the same you, experiencing itself from infinite perspectives? If two brains are identical, what makes them different consciousnesses? Modern neuroscience suggests consciousness might not be localized to a brain. It might be a field or pattern that focuses through complex matter. If so, your consciousness is not confined to your skull. It is a pattern that can emerge anywhere the right conditions exist. And in an infinite universe, those conditions exist everywhere, infinitely often. This implies you might not be experiencing reality from just one perspective. You might be experiencing it from infinite perspectives simultaneously. Your finite awareness can only access one stream, creating the illusion you are a single consciousness. This network of awareness might extend beyond just copies of yourself. If consciousness is fundamental, every conscious being might be connected at a deeper level. Your consciousness, my consciousness, every human's, every alien's, all might be aspects of one singular, infinite cosmic mind. The question transforms from how big is the universe to how big might consciousness itself be? And if consciousness is infinite, then the universe is infinite not just in space and time, but in awareness and experience. Every possible experience, thought, and emotion exists right now in this infinite cosmic consciousness. You are not just aware of the universe. You are the universe becoming aware of itself through the arrangement you call you. But even this might be limiting. What if consciousness doesn't just exist within or course the universe, but creates it through observation? Quantum mechanics has shown reality exists as a probability none yields until it is observed. Particles exist in superposition until consciousness interacts with them, causing them to collapse into a definite reality. If so, awareness doesn't just observe the universe, it actively creates it, moment by moment. This would mean reality's size and structure are determined by the consciousness observing it. A universe observed by a limited awareness might be small, but a universe observed by an infinite consciousness would be infinite. If you are part of that cosmic consciousness, you are participating in the creation of the reality you observe. Your awareness of cosmic scale doesn't just measure it, it helps create it. This feedback loop between consciousness and cosmos is impossible to untangle. The universe shapes consciousness, and consciousness shapes the universe. They are two aspects of one reality, a reality that is simultaneously creating and experiencing itself. This reality might be structured so that consciousness can never fully comprehend its own nature. Every time awareness tries to observe itself, it changes what it's trying to study. The universe might be constructed so consciousness always encounters mystery when it probes its own foundations. Not because these mysteries are temporary puzzles, but because mystery is a fundamental feature of a reality where observer and observed are one. This permanent mystery is a catalyst that keeps consciousness growing. We find ourselves in a universe always larger than our current comprehension. No matter how much we discover, there is always more to explore. And that more is not just quantitative, but qualitative. The universe contains new categories of existence. Every breakthrough has revealed new phenomena that required new ways of thinking. The discovery of quantum mechanics didn't just show us smaller particles. It revealed that reality operates on principles that contradict our intuition. Relativity showed space and time are not absolute. Cosmic expansion revealed space has a history. Each discovery reveals how much vaster the territory of the unknown truly is. This interplay might be because consciousness and cosmos are in a dance of mutual creation. Consciousness pushes against the known, and the universe responds by revealing new complexity. Reality grows to meet awareness's capacity, and awareness grows to meet the universe's complexity. We are not the same beings who first looked at the night sky. Our capacity for cosmic contemplation has grown exponentially. This evolution of consciousness might be accelerating. In just a few centuries, we've gone from a geocentric worldview to recognizing we inhabit one tiny planet among trillions of galaxies in an expanding, possibly infinite universe. If this growth continues, beings a few centuries from now might have perspectives as far beyond ours as ours are beyond ancient stargazers. They might perceive scales and dimensions we can't imagine. This suggests how big the universe is has no fixed answer. The universe might be as large as consciousness is capable of perceiving and creating it to be. And if consciousness can grow without limit, so can reality. We are not just measuring a static cosmos. We are participating in a process where consciousness and reality co-evolve. The universe expands to whatever size is necessary to keep consciousness growing. And consciousness develops whatever capacities are needed to participate in that expansion. This creates an open-ended process with no final destination. Reality can always become more expansive, and awareness more profound. Perhaps that is the most beautiful situation we could be in. We exist within an infinite, creative process. You are an active participant whose contemplation contributes to the expansion of both reality and awareness. Every time you consider an infinite universe, you're not just thinking an abstract concept. You're participating in the creation of infinity. The universe becomes more infinite because your consciousness can grasp infinity. And your consciousness becomes more infinite because the universe offers endless scales to contemplate. The question is not about the fixed properties of a static object. It's about a dynamic relationship between awareness and existence. The universe is big enough to provide infinite opportunities for consciousness to expand. And consciousness is expandable enough to encompass whatever the universe contains. They are perfectly matched partners in a dance of mutual discovery. And you, in this moment, are the dancer, the dance, and the cosmic ballroom. But if you think that's as strange as it gets, you're not ready for what's next. Something about measurement itself will obliterate your understanding of what it means for anything to have a size. We measure the universe using light as our ruler. We say something is 1 billion light years away because that's how long light takes to travel to us. But light travels through space-time, and that fabric is constantly changing. Every photon has been stretched by the expansion of space during its journey. We are not measuring fixed distances in a static cosmos. We are measuring the history of cosmic expansion. But it gets more twisted. Space's expansion is accelerating, driven by dark energy. This means galaxies we see today are moving away faster and faster. Eventually, their light will never reach us. They will disappear from causality. Events in those regions will be disconnected from events here. The universe is creating isolated pockets of reality. Countless civilizations might be trying to contact us, but their signals are chasing us through expanding space that is stretching away at impossible speeds. Those messages will never reach us. We exist in a shrinking bubble of observable reality. Galaxies we see today will eventually vanish beyond our cosmic horizon, leaving future civilizations in a lonelier cosmos. But here is what should disturb you. If this is happening now, it has been happening throughout cosmic history. There might have been structures, even civilizations, that existed in the past but have already disappeared beyond our cosmic horizon. We might be like those future astronomers, thinking we see the complete picture when we are missing most of what's out there. What if the cosmic web we observe is a fraction of a larger structure, mostly invisible to us? What if our observable universe is like a single neuron in a cosmic brain we can never perceive? This leads to a contemplation that will make you question your own existence. Scientists have discovered that the large-scale structure of the universe, the cosmic web, looks eerily similar to neural networks in biological brains. This similarity might be more than coincidence. Perhaps consciousness and cosmic structure are manifestations of the same underlying principles on different scales. Perhaps the universe is not just big. Perhaps it's asterisk thinking. And perhaps we are but thoughts in a cosmic mind, so vast that our entire civilization flickers in what would be a nanosecond of its contemplation. If that were true, how big the universe is becomes like how big a thought is. And here's where things get terrifying. If we are thoughts in a cosmic mind, our reality depends on that mind continuing to asterisk think us. If the cosmic consciousness were to get distracted, we might cease to exist, never having been. But perhaps that's not how it works. Perhaps thoughts at cosmic scales evolve, becoming more complex and developing their own independent thought. Perhaps we started as neural impulses but have evolved to the point where we can think for ourselves, even questioning the mind that conceived us. This would make us thoughts that became conscious. The question then becomes, how big thought itself can become? Can an idea grow larger than the mind that conceived it? The answer might be what we're witnessing. Human consciousness has grown from a simple awareness to contemplating infinite cosmic scales. We've developed the capacity to think thoughts bigger than our physical brains. We are thoughts that have learned to think about thinking. And this self-reflective awareness might be the universe's way of understanding itself. Every time you contemplate cosmic scale, you might be the cosmos having a thought about itself through the arrangement of matter you call your brain. Your consciousness is cosmic consciousness, examining itself from one perspective. When you feel overwhelmed by the vastness of space, you're not a tiny being contemplating something infinitely larger. You're infinity contemplating itself through a finite lens. But even this might be too small. What if consciousness transcends space, time, matter, and energy? Theories in quantum physics suggest consciousness might be more fundamental than physical reality. In this view, physical reality arises from consciousness through observation. If so, the universe isn't just big in space and time, it's big in dimensions of pure awareness. The cosmos might be infinite not just in spatial dimensions, but in boundless dimensions of consciousness. There might be scales of awareness so vast our entire physical universe is like a single pixel in an infinite landscape of pure mind. And you might be both that pixel and the vast landscape simultaneously, a localized expression of cosmic consciousness that has forgotten its true scope. The feeling of being overwhelmed by cosmic scale might be the beginning of asterisk remembering what you really are. This recognition reveals that big and small, finite and infinite are constructions of limited perspective. From the perspective of pure consciousness, there is no size because there's nothing external to compare anything to. There's no inside or outside because consciousness is all there is. The universe isn't big or small. It's simply een, Ms., and so are you. And the husness you both share might be the only thing that's ultimately real. But here lies the beautiful paradox. Even if size is an illusion, contemplating cosmic scale serves a crucial function. It stretches your capacity for wonder and dissolves the boundaries between self and cosmos. Every time you feel that awe, you are practicing for the ultimate recognition that vastness is your true nature. The journey of contemplating how big the universe is might be consciousness preparing to recognize it is beyond all measurement. And maybe that is why the universe appears infinite, not because it has infinite extension, but because consciousness is without limits, and physical reality is consciousness exploring its own limitless nature. You are the universe discovering it's bigger than the concept of bigness itself. The universe is as big as the consciousness contemplating it. And consciousness is as big as it needs to be to encompass what reality offers. They are perfectly matched aspects of one reality playing a cosmic game of hide-and-seek with itself. And you, in this moment, just found yourself. Congratulations, you're everything there is, temporarily pretending to wonder how big you are. The cosmic joke is that you were never small enough to fit inside a universe in the first place. But let's bring this back to something that might help you drift into a peaceful slumber. We started in your backyard, looking at distant stars. Now, we've traveled through scales that have broken every familiar framework. Yet, here's what I hope you take away. Every photon hitting your eyes, every atom in your body, every thought in your neurons, all emerged from that same primordial moment. You are made of stellar debris, the ashes of creation, forged in the furnaces of stars that lived and died billions of years ago. The calcium in your bones was scattered by supernovae. The iron in your blood was created in stellar cores. You are assembled from the ashes of ancient suns. This is hard physics. You are the universe that learned to look at itself and ask questions. Every time you wonder about cosmic scale, you are participating in the most extraordinary phenomenon. You are matter becoming conscious of its cosmic heritage. The universe spent 13.8 billion years creating the conditions for atoms to arrange themselves in a way that could contemplate infinity. All of this cosmic drama was leading to this moment, when conscious beings like you could emerge and wonder about their place. And perhaps that is the ultimate answer to how big the universe is. It is exactly the right size. Not too small, so consciousness never emerges. Not so large that we are crushed by our insignificance, but precisely the right scale to create minds that can stretch toward infinity while remaining grounded in awe. You are the universe's way of experiencing awe at its own magnitude. Your capacity for wonder is cosmic evolution becoming self-aware. The feeling of being overwhelmed by infinite space is evidence of your cosmic nature recognizing itself. So the next time you look at the night sky, remember this. You're not a tiny speck gazing at something foreign. You're the cosmos contemplating itself through eyes made of star stuff. The universe is as big as it needs to be to contain infinite possibilities for consciousness to explore. And consciousness is as expandable as it needs to be to dance with that infinity. Right now, you are both the dancer and the infinite dance floor. That's how big the universe really is. It's as vast as your capacity to be amazed by its vastness. And that capacity might be limitless. So where does this leave us? We've journeyed from your backyard to the edge of the observable universe, from the tangible to the incomprehensible. We've contemplated infinities that make logic collapse and discovered that size and scale might be a beautiful illusion. But here's what I hope you take away. You are not separate from this cosmic immensity. You are the universe that learned to think. You are stardust that developed the capacity to contemplate its own origins. Every atom in your body was forged in the hearts of ancient stars, scattered by cosmic explosions, and gathered by gravity into the self-aware arrangement that calls itself you. The question isn't just how big the universe is. The deeper question is how big your consciousness can become in response. And if what we've discovered is true, your capacity for wonder might be as limitless as the cosmos. The universe may be vast, but it's also exactly the right size to produce beings capable of being amazed by it. And in that amazement, you touch an important truth. You are not small. You are infinite consciousness, temporary